Okay, so good afternoon, everyone. And so I was asked to give a monographic lecture on quasi-periodic oscillations, which is indeed one of my favorite subjects. And I've been working on it on and off for many, many years. And I must confess that it took me a while to reassemble materials and ideas around what has been happening more recently than the previous extensive presentation I gave on this subject. So let me start by listing a few reviews. Listing individual papers is nearly impossible. You will find some in the slides, but I mean, there are many hundreds of papers related to QPOs in X-ray binaries. So perhaps the main actor in this field of research, at least from the point of view of the observations, is Michiel van der Klis. And he has written a number of reviews on the subject. And I don't quote them here individually because you will find them referenced in the other reviews that I've written more explicitly down here. In particular, I would recommend you to, especially those of you who might be interested also in the physical processes that might be relevant to QPOs, not just the frequency identification and so on, which will indeed be the main subject of my presentation today. I would recommend them to have a look and read this Ingram and Motta review that is indeed extensive, very nice, and very pedagogical too. Okay, so let me start with a few basics. The students have already seen a few slides from this presentation during the earlier lecture, much more compressed lecture that I gave on strong field diagnostics in the fall, or in the winter rather. I was saying, let me begin by reminding you of some of the basics. Okay, first of all, we will be talking about QPOs only in X-ray binary systems. By now, QPOs have been observed also in a couple of AGNs, active galactic nuclei, supermassive black holes, although we know very little about this phenomenon. And perhaps also in some either strongly accreting neutron star or intermediate mass black holes in the so-called ultraluminous X-ray sources. In the latter case, they hold some analogies with the more classical QPOs from X-ray binaries, but today we will be talking only about QPOs from X-ray binaries. So let me remind you that accretion is indeed the most powerful, the most effective way of producing energy. Once you get mass inflow into towards a collapsed object, you can liberate enormous fractions of the rest mass energy of the matter that's accreting. And indeed, it is especially so if you have a situation in which the accreting matter is endowed with some angular momentum, such that an accretion disk can form in which materials gradually spirals in towards the black hole or towards the neutron star, in which case efficiencies of up to almost 50% can be attained. This is one of the best ways we have to access the strong gravitational field regions of black holes, especially in a regime in which the space-time itself is stationary. These days, we have seen lots of results from gravitational waves, and of course, those gravitational waves provide us with information on strongly varying strong gravitational fields, which is of course exceptionally interesting. But instead, when we are talking about accretion phenomena involving very small amount of matter, because of course the matter in an accretion disk is, at least in this accretion disk, is always much smaller than the mass of the compact object. We are dealing basically with the space-times that are constant, and we just see the effects of matter moving, of a test particle, even ideally moving in the field of these compact objects. Of course, when dealing with astrophysical phenomena of this kind, we are not dealing with clean systems, in the sense that There are a variety of effects, including plasma, radiation processes, magnetohydrodynamics, fluidodynamics, that can complicate the phenomena that we observe. For instance, can affect in a sizable manner, in a sizable way, the motion of matter as compared to simple geodesics. So we always have to keep these potential effects in mind and try and study the system through those features that they display that look the cleanest possible. But of course, we are dealing with, in general, complex phenomena. And indeed, in preparing this lecture, I've tried to separate as neatly as possible the phenomenology of QPOs, which is really complex, from the interpretation of the QPOs. So this lecture, it's longer, in a sense also difficult to follow, because the complex phenomenology of QPO is something that is difficult to address in all I mean, in some detail, let's say. And even if I will concentrate mostly on the frequencies of the QPOs, there is a vast range of other phenomena that have been studied that relate to QPOs, including, for instance, the amplitude, the underlying process in terms of amplitude variation, frequency variation, and so on. Delays in the QPO variability across different energies, spectral behavior, and so on. So I will try to use as little as possible information about these other things in order to describe what has emerged in terms of the frequency identification of the QPOs. Okay, let me begin by a bit of history. So the idea of quasi-periodic signal from accretion disks is indeed very, very old. It's 50 years old by now. It was proposed by Sunyaev back in 1972 that it should be possible to discriminate between the cases where a Schwarzschild or the Kerr metric prevails based on the fastest QPO signal arising from a disk at its innermost stable circular orbit. Let me remind you that the relativistic potentials, effective potential, have this form, at least in the Schwarzschild case, where there is this third term here, which is general relativistic in origin, and causes the behavior of the effective potential to be drastically different from the classical one, because at short radii, you see that you don't have this, this effective potential growing to infinity any longer, but rather it generates a peak and a valley. And as you decrease the specific angular momentum of the particles that you are considering, you see that this peak decreases progressively because of the increasing effect of this term. And eventually you get, it leads to an inflection point rather than a minimum in this valley. And this inflection point is what is usually called the last stable circular orbit, or equivalently, the innermost stable circular orbit. This is a powerful diagnostic of general relativity indeed. And this is plotted, as I've said, in a Schwarzschild space-time. But if you consider a Kerr space-time for a co-rotating disk in the equatorial plane, you can easily see that the radius of the ISCO, as measured in m units, meaning gm over c squared, is no longer 6 as it is in this case, but rather the ISCO, the radius of the ISCO, gets to be smaller and smaller and smaller until it basically touches even the event horizon for maximally spinning black holes. Well, Rashid Sunyaev back in 1972 was referring exactly to this. If we are capable of identify QPO signal arising from the motion of matter at ISCO, and we have an independent way of estimating the mass of the black hole, we can in principle deduce whether the black hole is a Schwarzschild or a rotating Kerr black hole. Well, some years later, Bill Sturger calculated even the characteristic signal that would be expected from matter that would be spiraling in from the ISCO inside the black hole, and therefore the type of quasi-periodicity is just a few cycles, in fact, before the matter crosses the event horizon. This just to emphasize that the idea of quasi-periodic phenomena from accretion disk in a very strong field regime is an old one, and a very interesting one since those years. However, observation did not find anything for more than 10 years. And in fact, it was back in the 80s that through observation with the European Space Agency satellite EXOSAT, the first QPOs were found. These were the so-called low-frequency QPOs. These low-frequency QPOs are represented in this much later set of power spectra that were obtained in the late 90s with a much larger area instrument on board the Rossi X-ray Timing Explorer. But let's concentrate for now on these features here. So these are 3 power spectra from a source, and this is a neutron star, presumably with no dynamically relevant magnetic field, so no magnetosphere. And you see 3 power spectra of its light curve obtained for 3 different intensity levels of the source. Well, back in the 80s, basically the rightmost part of this diagram could not be studied. So what people would see from sources like this, not precisely this one even, would suggest this noise component towards low frequency with a characteristic shape that rose and then flattened. And then somewhat to the right of it, in the declining part of it, there would be these broad power spectrum peaks that testify to the presence of quasi-periodic oscillations. So these characteristic frequencies of tens of hertz typically, or even less, and were observed in the 80s indeed from a number of sources. One thing was apparent immediately, that these frequencies were slow. These frequencies were much slower indeed than the maximum frequencies of the orbits close to the ISCO, for example, for a neutron star. If you are a DISCO for orbiting a DISCO around a neutron star, basically you would be traveling with a frequency of something like 1500 hertz, above 1 kilohertz. Here we are dealing with tens of hertz. So it was clear that the phenomenon could not reflect simply the orbital motion of matter in the vicinity, in the very vicinity of these neutron stars. Well, black holes displayed in a few cases also QPOs that were slow, also in the 80s, and also in this case were much longer, much slower frequencies or much longer time scales than the dynamical time scales in the vicinity of a black hole. And these QPOs were more difficult to observe. In general, we know today that the QPOs are much more pronounced, stronger, frequently observed in neutron stars, X-ray binaries, rather than in black hole binaries. We don't know why, but nature seems to work this way. So in general, black hole QPOs are more difficult to observe. So let me say a bit more about, of course, I should mention since now that high frequency QPOs have also been observed from black hole systems. Here is a list. This was compiled some years ago. There will be a more extensive more extensive table that I'm going to show you a bit later. Okay, these are the power spectrum of slow QPOs from black holes. Okay, well, there is not a single type of slow QPOs from black holes and neutron stars. In fact, 3 different types have been found and described in detail. But let me show you a few examples. This is the same source. It's a black hole system, GX339-4. And at different times, doing different observations, it shows different QPO modes, which are not really distinguished by the frequency itself, but rather by, for instance, look at in this case. Look in this case down here. You have here the QPO peak and relatively little noise. But in this other observation, you have a very large amount of noise. You have the strongest QPO peak, and you have here the fundamental, the second harmonic and the fourth harmonic of the signal. In a different interpretation, you have the subharmonic, the fundamental, and the second harmonic. So it's signal that is rich in harmonic component. These are called type C, these are type A QPO, and there are even type B, which have somewhat intermediate characteristics. Of course, one way of classifying them is based on the characteristics of the power spectra. But in general, I don't know what's happening. Oh boy. I'm sorry, something was going wrong. Can you still hear me?
Yes, we can hear you.
There was something wrong with my computer for a few seconds. I'm sorry for the interruption. Where was I?
We heard everything, I guess. Just the slides were moving.
I'm afraid I deleted some slides as I was pushing. No, actually I didn't. Well, this I was saying, I'm sorry. This is a classification based on the properties of the power spectra. Well, there is something that is always based on classification of power spectra. This is a somewhat different representation, which we don't have just power on the y-axis, but power times frequency. Okay, so the overall effect is the one of flattening the appearance of the power spectra. And here you see the same 3 types of black hole QPOs that I've shown you, type C, type B, and type A. And through extensive comparison with neutron star system, it was possible to put these 3 groups into a one-to-one relationship with the low frequency QPOs observed in neutron stars. Terminology is different. Type A corresponds to flaring branch oscillation, type E to normal branch oscillation, type C to horizontal branch oscillations. So I don't want to go too deep into this type of phenomenology. Also because most models, as we will see, make an effort to interpret the HBOs in neutron star and the type C QPOs in black holes. These QPO modes, these low frequency QPO modes, the top 4 one that you see here, are much more difficult to interpret, and we have just a few ideas perhaps for some of them. So most models, once again, address this type of QPOs, low frequency QPOs, the ones that have a strong red noise associated to them, red noise that shows a clear knee at a certain frequency below the QPO frequency. And this is observed in both systems. At the same time, the QPO peaks in this type C and HPOs oftentimes come in pairs, which are harmonic. Okay, so testify to the presence of a quasi-periodic oscillation that has some harmonic component. Well, indeed, this, I mean, part of the evidence for this distinction is based on the power spectrum characteristics, but the other part is based on the association of spectral and intensity characteristics of these sources. Again, I'm not going to describe this in detail, but just to emphasize that these classifications are really strongly founded on observations and do use different diagnostics. I mean, people have used different diagnostics to make this conclusion solid. By the way, perhaps it's worth spending some words also on this. Here in color code, you see the different types of QPO, low frequency QPOs. And basically this pattern here that we see are what these sources do, black holes and neutron stars, in a diagram that is hardness ratio on the x-axis and Eddington luminosity on the y-axis. So these sources are all variable. Sometimes they're even transient. And as you can see from this diagram, in most cases, we observe the type C QPOs in black hole candidates, whereas the A and B types are much more rarely observed. And the same story holds for neutron star systems. In the vast majority of the cases of the observation, we see the horizontal branch oscillations, and we don't see instead the flaring and the normal branch oscillations. Okay, this identification is further, I want to insist on this because, I mean, it's not that, people have investigated this particular subtype of low frequency QPOs because they didn't like the others, but just because there is a clear association between the different low frequency QPO modes based on different diagnostics. These are even two more diagnostics. One is based on the amplitude, and another one is based on a peculiar spectral diagnostic that I will not describe here. But I mean, the pattern of these QPOs are really, their classification is really based on very solid grounds. Okay, now we haven't talked about the properties of QPO, low frequency QPOs, in particular type C and HPOs, the two ones that the models address in particular so far. But let's consider the frequency. Now in this plot, let's concentrate on the left part of this plot. We see basically the QPO frequency for both neutron stars and black holes in this diagram, which are plotted with slightly different symbols described here in the caption, plotted versus the break frequency. So in other words, in this plot, you see the break frequency of the noise and the frequency of the QPO peak. And it's absolutely remarkable that once you plot these two frequencies, they all lie on the same line pretty much. You see, no matter whether they are neutron stars or black holes, there is a clear evidence, very strong evidence that even the frequencies are correlated in the sense that in absolute terms they could be different because, for instance, the black hole tend to have the black symbols here are black hole QPOs and break frequencies. The black hole systems tend to have lower QPO frequencies. Neutron stars tend to have higher frequencies. Well, but nevertheless, they all lie on the same line. So there is a clear, besides the characteristics that allow to draw analogies between the different types of low frequency QPOs, there are also, clear quantitative similarities between the frequency involved in these type C and HPO low frequency QPOs from neutron star and black hole systems. One thing that has emerged very clearly in recent studies, this is one of the few things that I will say about other diagnostics, is that the type C QPOs and HPOs, so the ones that I've talked about, are generated by some geometrical effects. We have much evidence for this. These are two different pieces of evidence. Here you see the fractional root mean square amplitude of these QPOs in as a function of the centroid frequency. Okay, this is just for black holes, but you see that in higher inclination systems, which are here plotted in blue, the average of these is plotted in blue, of these systems is plotted in blue, is as a larger amplitude than the low inclination system. So whenever we see these black holes from high, these accreting black holes from higher inclination, well, the amplitude of these QPOs is larger, considerably larger. And this is a similar effect that is found in the delays between the variation associated with the quasi-periodic oscillation at different energies. They have opposite behaviors for high inclination system and for low inclination systems. This is part of the evidence, and there are also other evidences. I will come to another one, very important one at the end of this lecture, that indicate clearly that the type C QPOs and HPOs are indeed generated by geometrical effect. They are strongly dependent on geometry. Okay, let's now come to the higher frequency QPOs. Now, this is again the same diagram we've seen before. And in later observation with the Rossi X-ray timing explorer, which has a much larger area instrument, also higher frequency QPOs were seen. Again, in this system, 1728-34, which is a neutron star system, you see that there are twin QPO peaks at a frequency that is this lower power spectrum, something like 700 and almost 1,000 hertz. And the two frequencies move towards higher frequency hand in hand. In this specific case, as the luminosity of the source, and therefore probably the accretion rate onto the neutron star increases. Okay, so you can see a general trend that the HPOs tend to vary. This is a log plot, by the way, in frequency. So the HPOs tend to show a more marked frequency increase, whereas these two seem to go hand in hand. I mean, their separation, we will see in a second, is not exactly constant, but nevertheless, when one goes up, the other one goes up too. So this is what we usually call twin killers QPO, or simply high frequency QPOs from neutron stars. And this is their general behavior. Let me tell you a bit more about these high frequency QPOs instead. We are dealing now with phenomena about 1,000 hertz that are indeed comparable to the orbital frequency of matter close to the ISCO of a neutron star. So when these were found in the late 90s, it became clear all of a sudden that finally phenomena occurring very, very close to the neutron star or to the black holes, as we will see in a second, were indeed observed. Okay, let me tell you a bit more about these frequencies. Okay, this is a list of sources. In the first, they are all neutron stars. And the first group is the so-called Z sources, high luminosity group. This one is the so-called atoll group, which involves lower luminosities. And these values that you see here represents the range over which the QPOs are observed to vary in each of these individual sources. So for instance, this COX-1, the brightest X-ray source in the sky, the green QPO that I've marked here in green. This is a color code that red, green, and blue that's meant to reflect frequency. Unfortunately, is not used consistently across all these transparencies. I was saying these numbers represent the range over which QPOs are observed. And the lower frequency kilohertz QPOs in COX-1 have this range, and the higher frequency ones have instead this range. Their separation varies between something. So if I do nu2 minus nu1, well, I obtain values that are between 307 and 237 or something like that. And you can see that indeed most of the sources have been observed to display QPOs over a range of frequencies that's quite variable. I mean, look at this, for instance. They involve a factor of 3 change in frequency. Well, in some cases, we have evidence that this separation of the 2 peaks stays more or less constant. In other cases, we have clearly very significant variations. See here from 300 to 200, same here. This involves a slower variation. Now, the interesting thing is that some of these lower luminosity neutron star systems display also a phenomenon during X-ray bursts, which are thermonuclear bursts on the surface of these neutron stars, that are called burst oscillations. So in essence, we see a phenomenon that involves, again, oscillations that are not strictly periodic, but these power spectrum peaks, they are not delta functions, as you can see, but they are much, much narrower than the one that are seen in the power spectra I was showing you before. And in those few cases in which these systems that do show this burst oscillation during type burst, and at the same time they possess a magnetosphere from which we see coherent oscillation that we can be certain are related to the rotation of the neutron star. We know that the burst oscillations occur either at the spin frequency of the neutron star, close to the spin frequency of the neutron star, or very close to half the spin frequency of the neutron star. Okay, so in other words, the burst oscillation in a number of systems, in a few systems, I'm sorry, in which we have independent ways of measuring the neutron star spin because they possess a magnetosphere. And we see that either the burst oscillation is equivalent to the spin of the neutron star, or the burst oscillations are twice the spin of the neutron star. Let's see a few examples here. Well, I think I've said the last thing wrong, but let me clarify it here. For instance, in this case, KS 1731 minus 26, you see that the separation of blue minus green is 260 Hertz, but instead the burst oscillation frequency is twice that. So this is the true neutron star spin frequency, and the separation seems to be close to half that. Well, this indicates that the spin of the neutron star has some role in generating this the separation of these two frequencies, at least in some cases, but still we don't have a full understanding of that. None of the model really addresses this issue in a satisfactory fashion. In this plot, I show you again, as a function of the blue frequency, meaning the frequency of the highest frequency QPO. So on the x-axis, you have the blue QPO frequency, and on the y-axis, you have blue minus green. And you can see that they all sit around 2 to 350, 260 Hertz separations, at least these systems. But the separation is not constant. Look, for instance, at the case of these X's here. You can see that in these X's show a clear behavior decreasing. So as if the separation of these two peaks would tend to decrease for increasing frequencies. Another case pretty apparently are the plus symbol here. This is cox1, same story. Separation tends to decrease. Of course, the spin frequency cannot change for the neutron star on the short time scales on which these observations are made, hours or variations that took place in days or something like that. No way of changing the spin frequency of the neutron star over such a short range of time scales. So in essence, the separation seems to be related in some cases to, although not in a precise fashion, to the spin frequency of the neutron star, but certainly that's it's not the only mechanism that determines their separation, because within individual sources we can also see pretty large variation in their separation. Okay, well, this is another slide basically summarizing what I've just told you. Oops, I don't know what this line comes from. But anyway, what about high frequency QPOs from black hole systems? Well, they are found in just a few cases. You see, in neutron star, we had plenty of observations of systems, more than 25, almost 30 neutron stars now display this phenomenology. In black hole system, it has been much more difficult to find these few QPO that have been observed. In some cases, we have seen high frequency QPO in twins. Okay, so twin high frequency of QPOs are also found in black hole systems. Now, one thing that has raised a lot of interest about these QPOs is the fact that in some cases, their frequency ratio involves a small integer ratios, 3:2, or even 1:2. You can find some example here. These are approximated values. Well, perhaps the best known case is this one here. These are just approximate values, but once you take the uncertainties into consideration, realize that indeed in this case, the frequency ratio is consistent with the ratio 3:2. Look, for instance, the last source here, which is indeed a very peculiar source, but you can see that 34 and 67 are in a ratio of 1:2, and also, I mean, within the error, 27 and 41 are. So this idea, I mean, this fact that even though with large uncertainties, the frequency ratio of the high frequency QPOs from black holes are in this integer ratios involved with very low integer numbers, has driven the ideas about the number of models. Let me emphasize that sometimes, as we have seen, these QPOs are observed together, the low frequency QPOs, the type C QPOs from black holes, type C QPOs and high frequency QPOs from black holes. But only in one case, we have observation that are simultaneous of two high frequency QPOs and a type C QPO in a black hole system. Only one in all these years, just one of these cases have been observed. There are rumors that the second case has been found, but that's not published yet. There is a warning that I should probably emphasize here. I mean, in some of these fits that were made in some 20 years ago, I mean, when fit in this power spectrum with two peaks, the fitting function was forced to have the ratio of the frequency peak in the 3:2 or even 1, 2, and 3 ratio. So in a sense, that made several people suspicious about this finding, because of course, in order to determine whether the ratio is really that one, it's really, for instance, 3:2, or, well, you should let the fitting function take whichever values the data wants to take. So you cannot force the fitting function to be already in a 3:2 ratio. Otherwise, you just get what you put in, a 3:2 ratio. So this has raised some concern about some of these analyses. They've been repeated in several cases, and indeed, in some cases, not all of the ones that were reported originally, the 3:2 ratio and even the 1:2 ratio still holds in some cases. Okay, so far I talked about QPO peaks in the power spectrum, basically as defined, for instance, in this power spectrum of Scorpius X1. And you can clearly see that they are broad, low frequency HPO, it's harmonic, lower kilohertz QPO, upper kilohertz QPO. Well, they're relatively narrow. Okay, but still they are broad. I mean, they are not delta functions as you would expect for a strictly periodic signals. Well, in a study that was carried out by several people and culminated in this work of Psalti, Belloni, and van der Klis more than 20 years ago, it was demonstrated that in several of these sources, as they undergo state changes that are substantial, these QPO peaks tend to evolve into broader components. What are they? Noise components, peak noise components. I mean, it's a matter of terminology, but what they were able to show in this figure, you see examples obtained by the rescaling by frequency, the power spectra of different sources and aligning them artificially by placing the right frequency factor to align them. So, but just to emphasize that as their state change and their frequency of the QPO changed, well, gradually these QPO peaks tend to get broader and broader as their frequency decreases. Here you see, I mean, different factors. Well, actually they go the other way around. The frequency is lowest here and increases for these peaks here. And I was saying, you see that these peaks tend to get broader and broader, but still based on the feature of this power spectra, you can still identify the way they evolve. For instance, the green peak that does this, the blue peak that basically disappears, and the red peak that does this evolution here as the frequency decreases. Let me just emphasize that this once again is a representation in which the power spectrum has been multiplied by the frequency, so that it looks like some of the power spectra multiplied by the same factor that I've shown you before. Well, once you get this very large frequency variation interpreted within this scheme, you realize that you can assemble the variation of some QPO systems over an extremely large range of frequency. And that holds especially for the low frequency QPOs, meaning HBOs and neutron stars, and black hole type C QPOs. In this graph, these people, Psalti, Belloni, and van der Klis, assembled this figure in which they have the low frequency kilohertz QPO. So the green peak, the green peak here. Let me show this again. So on the x-axis, you have the green, the lower high kilohertz, the lower high frequency QPOs. Okay, so you have this frequency on the x-axis, of course, as it evolves in the way that we were showing before. And here you plot the low frequency QPO, which is the HPO for the neutron star, and the type C for the black hole system that are plotted here in red. I'm sorry that the color coding is not consistent, but nevertheless, once again, they all lie within a single correlation that extends for 3 decades in frequency, basically. And it is almost linear independence. You see, this is the kind of scaling that you can determine from a fit. And the same story, although for a much reduced frequency range, once you plot the blue QPO peak versus, the blue QPO peak versus the green QPO peak. Even in this case, you see that black hole systems, red, and neutron star system, blue, align. There are also some red systems here, which are not, some green systems. Oh, I'm sorry, I've said something really wrong. Forgive me. I must correct myself, really. Red and blue are neutron star systems. Green are black hole systems, okay? So this correlation holds for both neutron stars and black holes. These are black holes. And there are a few green points around here. Some green points appear from black holes, but the bulk is neutron stars. Okay, so these two correlations have become known as the so-called PBK correlation from the names of the authors. Okay. Well, this is, I mean, highly suggestive that a successful QPO model must be capable of interpreting also these variations. I mean, this very large frequency variation and associated variation that involve 2 or even 3 in some cases QPOs. Okay, so I'm now briefly summarizing the basic findings there concerning the frequency of the QPOs. So in this figure, you see a rough representation of the frequencies in this power spectra. So we have the HBO to represent really the HBO in neutron stars and the type C in black holes, which is one of 3 QPO modes that are found in these systems. And then we have instead at a high frequency, the lower high frequency QPO and the upper high frequency QPOs. So this is something like the paradigm of the power spectra that models try to interpret. So to summarize the phenomenology that I've tried to describe, especially about the frequency and the frequency behavior of these QPO peaks or broad noise components, well, there are very strong similarities in neutron star and black hole QPOs. Frequency variations in low frequency QPOs are very pronounced. These involve the type C and the HPOs. Frequency variations in neutron stars high frequency QPOs are clearly present and observed in many cases. It is not clear whether the high frequency QPOs that are observed also in some cases in pairs do vary or stay constant in frequency. Okay, so you remember when we talked about the frequency of the high frequency QPOs in black hole systems, we have talked about basically individual measurements, and there is slight evidence, but not really convincing, that each of these frequencies changes in time for a given source. So it is unclear at this time whether the frequency of black hole high frequency QPOs varies. Well, and there is this fact also very intriguing, that if you consider the evolution of this this relatively narrow QPO peaks here, they are broad, but still they're not very broad, as the state of these sources changes, they evolve into peak noise components, and that whose frequency correlates over a huge range of frequency. Again, if you consider the variations of the green versus the red, 3 decades in frequency, their variation, this one here, and about 1 decade in frequency variation if you consider blue versus green. So all in all, this is what the phenomenology concerning the different types of QPO modes, their variation and so on, that have been observed both in black holes and neutron star system have been considered in modeling this type of behaviors and phenomena. Okay, So if that is all right with you, I would stop here for a few minutes. And if you agree, we can reconvene at 17:05. Oh.
Okay.
Okay. Okay, so these are the basic characteristics that I'm asking you to keep in mind when we will be discussing models. Of course, when we discuss models, I mean, so far we have talked facts. Okay, it's not something that may depend on my personal inclination, on other people's inclination, and so on. From this point onwards, we try and talk about the models. And indeed, there is a very large variety of models that has been constructed or proposed for QPOs through the years. And I mean, of course, as always, in a sense, there is a burst of model proposals soon after new phenomena are discovered. These days, we are having bursts of models for fast radio bursts, for even for the so-called quasi-periodic eruptions that have been seen by now in 4 or 5 extragalactic X-ray sources. Well, 20 years ago, when this phenomenology that is summarized in this slide began to emerge, we saw really many models being proposed. They count by the tens by now. Okay, let me move on. So very early on, a generic model proposed for the higher frequency QPOs, I mean the blue peak, okay? So the idea, I mean, in a sense, goes back to the old Sunyaev idea, or even the Bill Sturger idea that I was talking about in the beginning. Well, basically that the very high QPO frequency might reflect simply the orbital motion of matter very close to the compact object. Well, you can work out some very simple numbers. Here is an example for a neutron star of 1.4 solar masses. Well, in scale, you see the radius of this neutron star, the radius here of an orbit at 1200 Hertz, the solid circle, and the dashed circles represents the ISCO. And this is a neutron star that's relatively compact. The idea is that, for instance, this is what you get for if you have a soft equation of state for a neutron star. The neutron star radius is relatively small, and the ISCO radius is somewhat larger than the neutron star body. Well, in this same case, in order to make a 500 Hz signal in the upper kilohertz QPOs, you would have to move just a little bit outside. I mean, here we're talking about perhaps 3 neutron star radii, here not even 2, okay? Well, you can indeed apply a very simple formula, because in the Schwarzschild metric, which is a good 0th order approximation for around neutron stars. In fact, it's a perfect approximation if you're dealing with a non-rotating neutron star. But if the neutron star rotates, there are other correction terms that play some role. Well, this is the kind of radius you would be at 15 kilometers for a 1 solar mass neutron star if you're traveling at 1000 Hertz orbital frequency. Well, the idea that came about very early on is that this variation in radius within the same source is what determine the frequency changes in the upper kilohertz QPOs, okay? This is a generic model, as I was saying, that basically was readapted immediately to black holes when the higher frequency QPOs were discovered in black hole system. Here you get another example in scale, which is designed to match the pair of high frequency QPOs that were observed in this case. This is the best determined case that we have so far, 450, 440 actually QPOs for the high frequency ones. In this case, this is a case I will be talking about later on. I should have written the source name here, which is Giro J1655-40, but I forgot. And which we know independently from optical observations of this system, of this binary system. Well, with a spin, say, of 0.3, which we will see later, it emerges out of a fitting of the QPOs, you would get this type of orbit, very close to these also in this case. Okay, so this immediately made it apparent that through these QPOs, it should be possible to diagnostic motions that do take place in very strong field around these objects, very close to these objects, in fact. Well, this is the result of a simulation from many years ago in which you see inhomogeneity in the disk, in an accretion disk. Of course, as they move around, they are expected to give rise to quasi-periodic phenomena associated to their orbital motion because of various effects, including relativistic beaming when they move towards you, and on the contrary, a weakening of their signal as they move away from you, for instance. But of course, there are other effects involved, like bending, redshift, transverse redshift, and so on. Okay, let's talk about some QPO models. Well, the models that I list here were developed very early on, some even in the 80s, when high-frequency QPOs were not discovered, that people were trying to devise models to generate lower frequency, tens of hertz, in dynamical regions, in regions in which dynamical timescales were much faster, of the order of 1,000 hertz. Well, these models, which I list here, are specific to neutron stars only because they involve the presence of a solid body, the body of the neutron star, or of a rotating magnetosphere, or the interaction between a magnetosphere, rotating magnetosphere, and the disk, and so on. So if you believe, well, I should probably say that the one that received the largest attention back in the 80s through the early 90s was certainly this magnetospheric and sonic point beam frequency models that were developed at different stages. The trouble with this model is that it basically failed to explain black hole QPOs, could not explain, in fact, black hole QPOs, the high frequency ones especially. And so it's pretty much not discussed, not considered anymore. Same story for this two oscillator disk model. And of course, also for neutron star oscillation models, because if you have a black holes, of course, you cannot have the same phenomena. So if we believe that neutron stars and black holes QPOs indeed have a similar origin because they displayed such a close phenomenology in their behavior, as we have shown in the first part of this lecture, and as it has been shown, really intense of studies, phenomenological studies of these QPOs, then we should pretty much abandon this model. Say they just address one part of the story, but we know that probably nature works in a very similar fashion for neutron stars and black holes. And since these are specific to neutron stars, probably they're not the right models. Well, concerning the other models, here I have inverted the slides, I'm sorry. Concerning the other models, they can be grouped even in families. Here are some family of QPO models that are applicable to black holes. Some have been developed also for black holes. Some models, for instance, involve disk oscillations and trapped modes. These were then discussed also in the context of neutron stars, so they can work in both. Disk work precession, same story. Parametric epicyclic resonance, relativistic precession models. These are family of models, not even models, okay? Not even simple models. Well, in all these cases, we are dealing with predicted QPO frequencies that are related to the fundamental frequency of particle motion in the strong field regime, okay? So let me go back to this slide, which should have been placed after the previous one. And the fundamental frequencies of particle motions are oftentimes described in terms of three fundamental frequencies. The frequency in phi, which is what we oftentimes called perhaps inappropriately Keplerian frequency. And the frequency in the theta direction and the frequency in the R direction. Okay, so these frequencies do coincide with each other for quasi for in a Newtonian gravity around the point mass. These three frequencies are all identical. But in general relativity, they show differences, remarkable differences, in fact, in the strong field regime. Here you see an orbit on the equatorial plane. These embedding diagrams are just used to visualize the perspective. Of course, they have no direct meaning in these cases. But you see, for instance, from A to B, that is a cycle in phi, Keplerian. But to reach again the same radius, you have to travel from B to C, so it takes longer, and therefore you have a lower frequency to attain the same value of the radius as before. So the radial frequency is lower. Now let's deal with a slightly tilted orbit, always around the Kerr black hole. From A to B, you again travel from the same phi you started from, and you go back to the same phi. So again, the phi frequency. But in order to get to the same theta again, you have to travel in addition from B to C. And that tells you that also the frequency in theta must be lower, because this takes a longer time than the phi frequency. So there is a hierarchy of these three frequencies, in the sense that the fastest one is the phi, then comes the theta, and then the R. And in fact, if you plot, for instance, the behavior of these three frequencies as expressed from the Kerr equations of motion in the general relativity, you get this plot here. This is for an 8 solar mass black hole with a spin parameter of 0.8, so relatively quite, relatively highly fast spinning black hole. Okay, this is the behavior of the phi frequency, Keplerian, azimuthal. This is the theta frequency, which is oftentimes called the vertical epicyclic frequency, and this is the R frequency, which is the radial epicyclic frequency. They are very different, of course, whereas in Newtonian gravity, they would just be identically at any radius. Well, we can see already several things from this diagram. First of all, there are specific radii, for instance, at which you have that these two frequencies are in a, for instance, in this case, in a 3:2 ratio. So this is 3 times the frequency. Nu theta is 3 times the frequency of the nu R. Same story here, except that in this case, nu theta is twice nu R. Well, through these fundamental frequencies, it's also possible to define the precession motion that you have in this type of orbits. You see, because in this case of a planar, of an orbit in the plane of the equatorial plane of the Kerr black hole, or even a Schwarzschild black hole, for instance, you have in this case, you have a clear periastron precession that is quite fast. Okay. Well, the rate at which the periastron precesses can be expressed, in fact, as the difference between the phi frequency and the R frequency. So it would be azimuthal minus radial epicyclic frequency. Similarly, the nodal precession that leads the plane of the orbit, the instantaneous plane of the orbit, let's see, around the Kerr black hole, of a tilted orbit around the Kerr black hole to precess, you see this precession angle moves at a frequency that's given by the nodal precession frequency, that is represented by the difference between nu theta, nu phi, and nu theta. So for instance, in this graph here, you see that nu phi minus nu theta, so this little double arrowed interval here, would represent the nodal precession frequency, whereas this longer double arrowed interval would represent the azimuthal minus radial epicyclic frequency, meaning the radial precession frequency, the periastron precession frequency, I'm sorry, periastron precession frequency. Okay. As you can see, of course, the periastron precession frequency is much larger than the nodal precession frequency, simply because these two frequencies are much closer than the distance between this one and this one. Okay. So through these three fundamental frequencies of motion, you can, describe in general also the precession phenomena that do take place in this orbit. Of course, an orbit that is slightly elongated like this one and slightly tilted like this one will undergo both things at the same time, both nodal precession and periastron precession at the same time. So it's a more complex type of motion. Okay, I spend some time illustrating these things here because they are relevant to many models. Okay. Okay. So one model that has indeed attracted a great deal of attention, it is indeed fascinating, has been proposed by people like Lodek Klushniak, Marek Abramovitz, further developed by Gabo Torok and collaborators through several papers and so on. And the idea is based on these resonances. This resonance and also other resonances. So in essence, at some specific radii in the disk, the radial frequency and the vertical theta epicyclic frequency attain simple integer ratios, I'm sorry, simple integer ratios, and therefore may resonate. In general, the basic type of resonance that people considered are this one, between nu theta and nu r. But in other studies, also resonances between nu r and nu phi, which aren't plotted here, but basically would involve this frequency and this one up here. So it would occur at a different radius, have been considered. Now, these epicyclic resonant models can explain black hole high frequency QPOs, especially those that are consistent with the frequency ratio 2 to 3 and 1 to 2, okay? Now, if you apply these models to this pair of QPO frequencies, you would obtain very high values of the spin parameters for the 3 to 2 parametric resonance, and somewhat lower value between 0.3 and 0.6 for force resonances, different types of resonances. Now, since these resonance conditions are attained also at specific radius, at specific radii, here, for instance, for 2 to 1, and here for 3 to 2 in the case that these two frequencies are involved. One of the predictions of the model is that the frequency of these higher frequency QPOs from black holes should either stay constant or jump from one resonance to another. Okay. This is relatively fine still for, quite fine for black hole sources, okay? So in essence, this model is designed to interpret the twin QPO peaks from black hole systems, but they forget about the lower frequency QPOs that we observe from black holes, in particular the type C QPOs that seems to be very clearly associated with at least with one of the two higher frequency QPO peaks, the green one, the lower frequency one. They also forget, I mean, they are also, sorry, and this is a problem with, this is an animated figure that was not very well done, I'm sorry, but anyway, in the PDF, you probably see the complete picture anyway. Okay, what about these 3-to-2 ratios in neutron stars, for instance? Well, in this graph, we plot two cases in which the 3-to-2 ratio has been very well confirmed. This is again GRO 1655-40, the one I was showing the power spectrum before, and another one which is J1550-56. Well, if you plot the frequency of the blue peak on the x-axis and the frequency of the green peak on the y-axis, well, and this is the line that represents the 3-to-2 ratio, you did see that for these two black holes, the things turn out to be quite nice. I mean, these points lay very close to the 3-to-2 ratio. Of course, there are also error bars, but the error bars are fully consistent with this line. When you consider neutron stars instead, you can clearly see that there are some values that are still consistent with these 3-to-2 ratios, but there are plenty of values that are not. So in its simplest version, the epicyclic resonance models works well for those few measurements of black hole system in which we have reasonably well-determined frequencies. And indeed, those frequencies are in a 3-to-2 ratio. But when we deal with neutron star, we clearly see that the resonance condition is not really verified, because this is these points here and this one up here are inconsistent with the 3-to-2 ratio. Well, this is why some tunable versions of the model have been developed that would allow to vary continuously the frequency of the QPO around the resonance condition. To me, it's not clear whether these tunable versions are indeed capable of explaining such large discrepancy. I mean, resonance is a phenomenon in physics that does occur, but over a limited range of frequency, but the range is usually very limited. But all in all, I mean, again, this is a fascinating idea, and it seems to work well for what it was developed. I mean, interpreting the higher frequency QPOs, and only those two, not the lower frequency QPOs, from black hole candidates. Okay. Then there are discoseismic models that have mainly been discussed mainly in connection to high frequency QPOs, but there are also applications to lower frequency QPOs. The models are more or less the same, except that there are some models which are better designed, better suited to interpret lower frequency QPOs. Well, I won't go through this list because it's really long. I don't want to spend too much time on it. We are dealing with the inertial G modes, global corrugation modes, warping modes, pressure modes, trapped non-asymmetric G modes associated to vertical P modes, non-asymmetric trapped pressure modes, and so on. And even some different ideas altogether that deal with, for instance, with the role of an accretion disk, which is endowed with a strong poloidal magnetic field that can generate ejections and so on. Finally, well, in these models as well, you deal mainly with some combinations of the fundamental frequencies of motions, the most frequently emerging out of these models being the ones that are related to the radial epicyclic frequency. Okay. I'm not an expert in this type of models, but I won't try to say much more on these. Surely they are designed, they appear to be well suited to explain some of the QPO peaks, but the frequency variation and the combination of the three peaks, to my knowledge, is not addressed by any of these models. Let me emphasize again as a final caveat that there are also models in which the oscillation frequency is not related to the fundamental frequencies of motion in general relativity. For instance, there are some models in which you have basically the some mechanism related to the extraction of energy from a rotating black hole that, according to some simulation carried out, for instance, by McKinney and collaborators, are capable of generating quasi-periodic oscillation. But the frequency of these QPOs has no clear relationship with any of the fundamental frequencies in the motion of matter close to these black holes. Excuse me. Okay, what I'm going to talk about, and here perhaps my own biases come in, is the relativistic precession model that several people, including myself, developed through the years, basically in very late 90s and early 2000. And that involves instead an attempt to fit the properties of all the three peaks together. So the nodal precession, the lower frequency peak, meaning HBOs in neutron star, horizontal branch oscillations in neutron stars, and type C QPOs in black holes, and the two higher frequency QPOs. And the interpretation that the model proposes is this one. The higher frequency QPOs is just the same as that has been vastly used in the generic interpretation. So the blue peak corresponds to the phi motion around the black hole or the neutron star. The green peak corresponds to the periastron precession frequency, and the red peak corresponds to the nodal precession frequency, or if you see more than one peak, perhaps the 2 times the nodal precession frequency. Okay, because again, this HBO horizontal branch oscillation peaks and type C QPO peaks oftentimes display multiple harmonics. So this is the basic idea of the relativistic precession model. It's a simple model. It's not that pretends to explain everything. It's just a model designed to interpret the basic frequency and their variations that we see from these 3 QPO peaks, especially when they are observed simultaneously. Okay, so let's talk a little bit about the different parts of this model and interpretation. The nodal precession frequency. Let us consider first this one, which is the slowest. Well, here we are talking about the nodal precession. So the plane of the orbit around the rotating body that is precessing. And in the case of neutron stars, we have we can use, in fact, the weak field expansion as a first approximation of this phenomenon, that it is the so-called lens-tearing precession frequency, something that was formulated a few years after Einstein developed the theory of general relativity. Well, and you have this very simple expression for the precession frequency as a function of the phi frequency, so the blue peak, okay? However, in the case of rotating neutron stars, and these neutron stars we know rotate at 300-400 Hertz, even 500 Hertz in some cases, therefore they are rotationally flattened, and therefore they have higher classical terms in their gravitational field that does generate itself nodal precession through classical terms. So one needs to correct for these effects. So the total nodal precession frequency is in fact the difference between the lens-tearing precession frequency, the nodal precession frequency predicted by general relativity, minus a classical term And they always tend to counter each other because the length steering precession is prograde, so it goes in the same sense of the precession, whereas the classical term is retrograde. So the two effects tend to, I mean, the second effect is a correction that subtracts from the first one. Oh, but one basic prediction is that at first order, you should have the frequency of the blue peak scaling, I mean, the frequency of the red peak scaling like the square of the frequency of the blue peak. So in this representation, this should go like the frequency of this peak within a source or within many sources should scale like the square of the frequency of this peak here. And indeed, this was observed very clearly. I mean, I remember, in fact, drawing this very first graph by hand because I didn't have a computer available when I did it. And I was really surprised that, I mean, this point, of course, there is also some bending here, so it's not perfect, but all in all, I mean, this is pretty consistent with the nu square dependence of the red peak as compared to the square of the blue peak frequency. Well, there have been subsequent studies. For instance, this is the same source I was showing the power spectra in one of the very first slide. You see that also this is consistent with the quadratic behavior, and this is some slightly different behavior of the second harmonic. And here you see many of the high luminosity neutron stars put together in this representation, and also in this case, it behaves like the square. The red frequency behaves like the square of the blue frequency. What about the relativistic precession model for the kilohertz QPOs, for the higher frequency QPOs in neutron stars? Well, here the interpretation again is in terms of the phi frequency representing the blue peak and the periastron precession frequency representing the green peak. Okay, so the idea here is that you have a slightly perturbed orbit in the R direction, slightly eccentric orbit, if you like, and we are seeing the speed at which the periastron of this orbit precesses. Well, based on the definition that we saw before, you can also think of the difference blue minus green. So nu phi minus nu of periastron precession. This by definition should correspond to the radial epicyclic frequency. Okay, so indeed in this case, several people prefer to plot instead of blue versus green, blue versus blue minus green. And this is the kind of plot that I've shown you before. Should go back for a number of slides to find it again. Excuse me. Here we go. So blue on the x-axis, and on the y-axis, blue minus green. So the difference between the two QPO, kilohertz QPO peaks in neutron star systems. Here we are again. Well, this can be expressed in terms of a really zeroth order model in application to neutron stars. So we assume a very low eccentricity, and we can specify the coordinate system as observed as usual from infinity for the blue frequency, which is identical to the expression here. Would you excuse me 1 second? I have really to answer this phone call. I apologize. Okay, can you hear me again? Okay,
Yes.
sorry for the interruption. Okay. Um, I was saying that basically we can find very simple expressions again for the phi frequency, which is the Keplerian expression in a Schwarzschild space-time. And for the Periastron precession frequency, the expression is also pretty simple. So when you subtract the two, you get this expression here, which gives you the radial epicyclic frequency. So this model is basically one free parameter, which is the M only, the mass. Well, if you plot this model against those points that I was showing before, you see that the general behavior, of course, it's not perfect again. For instance, look at these points. They don't really lie along this curve, but some others, like the plus that represent, for instance, cox1, if I remember correctly, yes, cox1 correspond to the plus symbol. Well, these are matched relatively well. But the thing that I find really, I mean, most interesting is that, this top here corresponds to the maximum of the radial epicyclic frequency. And when it goes to 0, here you are at disco, okay? So these three lines represent this very, very simple model, just as a function of mass, no adjusting of the normalization on the y and x axis. You have no freedom whatsoever, just the mass. And you catch quite well the general behavior of these points if the neutron star mass is relatively high, of the order of 1.8 up to something like 2.2 solar masses. Now, when this plot was made back in the late 90s, these values of the neutron star masses were considered too high. But now we have several neutron star masses for which we have values absolutely in this range. So, I mean, these values are no longer outlandish as they were 20 years ago. And one thing that was especially gratifying is that once the detailed study of the high frequency QPOs for Circinox X1 were made, another neutron star system. Well, actually, these are QPO and also broad noise components. So they are along the PBK correlation that I was showing you before. Well, these points from these sources seems to match pretty well the low frequency behavior of this predicted model behavior. Again, they do match pretty well this behavior, this expected behavior here. So these red points were added afterwards. I mean, nothing was changed in this figure, just the points became available and were plotted on top here. Okay, so let us consider a full application of the relativistic precession model to the HBOs and the kilohertz QPOs from one of these sources. Again, the one that I showed you in the very first power spectra that I showed you, 1728 minus 34. For this source, we know what the spin frequency of the neutron star is, because we see burst oscillation, and the spin is something like 364 hertz. Well, therefore, we constructed a more sophisticated model that was based on a numerical time for a rotating neutron star with a given equation of state, a relatively stiff equation of state. That was this one here. A mass of 1.93 solar masses. And we try not even to fit, but simply to adjust the values that we find from these calculations to the points that were measured. And this is what we obtained. This is the blue frequency. Here we have the HBO frequency, and here we have, again, the difference between blue minus green. And in this case, you see the interpretation of the different harmonics of the lower frequency QPOs correspond to twice the nodal precession frequency and 4 times the nodal precession frequency. And the behavior, quadratic behavior, is quite well respected here too. And this is the behavior for the higher frequency QPO. Certainly not perfect, but not even bad if you consider again, you are dealing with basically the mass and the choice of the equation of state as the only free parameters. Okay, but another, point that was pretty much in favor of this frequency identification of the relativistic precession model was the application to the PBK correlation. So let me remind you what the PBK correlation is. Should have duplicated these slides instead of going back and forth, but nevertheless, these are the this is the PBK correlation. So here you have the green frequency on the x-axis, and here you plot on the y-axis once the frequency of the HBOs and the type C from a few black holes at low frequency or very low frequencies. And here the same story for the blue plotted as a function of the green peak. Okay. Note that in this diagram, they originally plotted also a different type of QPOs from neutron stars, the NBOs, but these are not considered in the, these QPOs are not considered in the relativistic precession model, for that matter, in any of the models that we have talked about today. So when applying the relativistic precession model to this data, we remove this data simply because these are not part of the model. Let me go forward again. Here is the application of the relativistic precession model to neutron star system. So in this plot, you only see the points from neutron star QPOs, and here you see the points from the HPOs, the low frequency QPOs plotted versus the green QPOs. And here you see the blue QPOs plotted versus the green QPOs again. So the normal branch oscillation that lied here have been removed. Okay, again, this is the behavior that was calculated from the model for an equation of state, same equation of state that I've shown you before. And for a mass of 1.95 solar masses, I found 3 different spin frequencies of the neutron star. 300 is the solid line, 600 is the dashed line, 900 is the dot dashed line, and 1200, pretty much close to breakup, is the dotted line. Okay, again, there is quite some scatter. Probably we are dealing here also with the different harmonics of the HBOs, but the overall behavior of the model fits quite well the correlation of the PBK found. You see, and this is not surprising, because if you work out the, I mean, here you have strong field effects coming in. You see that this line bends, but if you work out what happens in a weak field expansion, well, by the time you are at 200 or 300 hertz, you are already in the weak field expansion, so you can just keep the first order. You find that the nodal precession frequency should scale like the periastron precession frequency, this one, to the 6/5. Okay, and this is matches quite well the behavior. And similarly, you see that the predicted phi frequency as a function of the periastral precession frequency is almost insensitive to the spin frequency of the neutron star. The 4 lines are all packed together. They're even difficult to separate from each other. And you see that once again, the behavior matches quite well the behavior seen in the relationship between the green QPOs and the blue QPOs. So this, in application to neutron star systems. In black hole systems, of course, it's even simpler, and you don't need to use a numerical space-time like the one that was calculated here again with the Nixer-Giulius chord. But you may just simply apply the curve metric. You have fewer points. But then again, if you are dealing with black holes with the spins of the order of 0.3 or something like that, moderate spin parameter value, you can see that all the points that you have in this graph, meaning relationship between the HBOs and actually also the broad noise, peak noise components of the PBK correlation here, representing the, I've called them HPOs inappropriately. This should have been called type C QPOs. And well, the overall behavior extended in this case over 2.5, well, actually 2 decades in frequency, is quite well reproduced by this behavior here. Of course, there are as many points in the case of neutron stars, of course, but still it looks quite promising. So let me show you instead here a complete application of the RPM, the relativistic precession model, to the best QPOs we have today from a black hole system. This is again GRO J1655-40. This is the higher frequency QPO peak, the blue one. This is the lower frequency, sorry, the lower high frequency QPO peaks, the green one, and this is the red one, okay? And you can see here the application of the relativistic precession model to all the data, all the QPO data from this source. Here, the representation is a bit different from the one we saw before, because in this case, you had on the x-axis the green frequency. In this case, on the x-axis, you had the nodal precession frequency, meaning the red frequency. Now, first of all, this looks like a perfect correlation and fit, but this is not the case. This is the type C QPO frequency plotted against itself. Okay, this with the goal of displaying the range of frequency over which the type C QPOs from this system were observed to vary. So quite a large range. Real QPOs here, and then evolving slowly into a broad noise component. So in a sense, reflecting the PBK behavior also in this case. Well, here you see the same story for the green peak plotted versus the red peak. There are several points here at the same frequency. And then these are the broad noise component, peak noise that you see here. And the the blue peak here, this point up here, and these few points here, okay? So this is the best case we have, because we have 3 QPOs simultaneously. It's the only case we know of. Perhaps there will be a second one soon, but you see, there is one occasion, single occasion in which 3 QPOs were observed at the same time, and this is the occasion and the 3 QPO peaks. I mean, these are plotted in a different scale, but they would show up here at higher frequency here. Well, so we can apply basically the relativistic precession model, something that was done in this paper by Motta and collaborators, to these frequencies. In this case, we have an additional piece of information, which is that we know independently the mass of the black hole, because this system has been studied in detail with optical observation. So by studying the way the companion mass orbits, projected velocities, inclination angles, and so on, it has been possible to determine by totally independent means that the mass of the black hole, the accreted black hole, is something like 5.4 plus or minus 0.3 solar masses. Well, through this fitting that is shown here with the relativistic precession model, where here is the nodal precession frequency, this is the periastron precession frequency, and this is the phi precession, and this is the phi frequency. You can see clearly that the fit is quite good. It leads to the determination of the mass of the black hole, that is 5.3 plus 0.07 solar masses, which is perfectly compatible with this value, and an independent determination of the spin of the black hole, which is close to 0.3, 0.29, in fact. Okay. So a similar application was made, but in this case, the one of 1555 minus 56, there weren't three simultaneous QPOs observed at the same time. So in this case, in the fit, unlike the previous case where the mass and the spin of the black hole were left free to vary, and it was found that the mass was consistent with the mass determined from optical observations. In this case, instead, the mass was held fixed at the value determined from optical observation, which are also available for this black hole here. Well, this is the kind of fit you would obtain, and in this case, all you can adjust is just the spin of the black hole, which turns out again to be 0.34. Okay, still pretty good fit to these values. Okay, so these are the two base cases we know of at this point. Okay, let me go back for a moment, because this is something that I will use to exploit a little bit what different authors have done. Let's go back to the low frequency QPOs, the ones that are by far the best studied. So HPOs in neutron stars, type C QPOs in black hole systems. Well, this is an example taken from two black hole systems. They are both black holes. And it's a spectral decomposition that was done for very slow QPOs, that type C QPOs that were observed in both of these systems, in which it was possible essentially to separate the spectrum, the energy spectrum from which the QPOs arise from the rest of the of the energy spectrum of the source. So the time average spectrum of the source is made by this. I'm not going to describe this in detail, but this is a characteristic spectrum of an accretion disk and a Comptonizing component that is present at higher energies. And you can also see some features that are originating from the reflection by the accretion disk. Reflection by the accretion disk. Well, if we, so this includes everything, but by singling out the spectrum of the QPOs, it was possible to see that the spectrum of the QPOs was like this, and it did not resemble at all the spectrum of the disk. In fact, it resembles the spectrum of the hotter part of the spectral component, the so-called corona, this illuminating central part of the accretion disk that we believe is present in virtually all of these systems. Same story here, although this fit is not as convincing in this one. Okay, so in other words, the variations that do generate the low frequency QPO, the type C QPOs in black hole candidates, almost certainly are generated by the central corona rather than the accretion disk proper. I remind you that in these systems, we have an overall picture that is like this. So this is a cross-section of the accretion disk. This is the central object. And there is an inner hot corona, very small, in fact, probably comparable in size to the east core, perhaps placed a little higher up or a bit lower down, or we don't know precisely the geometry of it. But nevertheless, this corona tends to illuminate the surface of the disk, which also emits its own radiation, but is considerably colder. And part of the radiation is reprocessed. Part of the radiation from the corona is reprocessed by the accretion disk. So the variability associated to the low frequency QPOs appears to be associated to the spectral component, and it's probably geometrical in nature, as we were saying before. It could be, for instance, the edge of the disk that's of an oscillating disk, of the oscillating inner region of this that is passing in front of the corona. Could be a movement or a precession of the corona itself. We don't know yet. But quite a lot of work has been done to try and use also the spectral information from the QPOs. Let me remind you that one of the features that is generated once you have this hot corona illuminating the surface of the disk is this very prominent, relatively speaking, of course, a feature here that you see, for instance, around 6 kV in the spectrum of this black hole candidate. This is a very large spectral range, but if you take an enlargement of this area, you would see that this iron line, and this is from another black hole X-ray binary, have this huge I mean, this very broad, extremely broadened profile, you see. The rest line energy of these transitions are 6.4 kV, and you see a profile that extends from almost 8 kV to 3 or 4 kV. And we see these things in a number of sources. This is, for instance, an active galactic nucleus. This is a pure galaxy. And I mean, this is another very powerful diagnostic that we have for the innermost regions of the accretion disks. And the idea is basically the accretion disk and the energy of the line that we see is generated by the different regions of the accretion disk. The ones that move towards us that generate a blue shifted, the ones that move away from us that are red shifted. And here you see the central black hole, and close to the central black hole, everything gets to be red, even the blue side of the disk, simply because the gravitational redshift and the transverse redshift in the classical equivalence, semi-classical equivalence tend to dominate. So this profile is basically generated by the different regions that emit the line profile. For instance, if you are at 400 gravitational radius, the profile of this region would be like this. As you move inwards, the profile gets broader and broader, 10 RG, 6 RG, and when you sum all the profiles together, you tend to get this profile here, okay? This by itself is a very powerful diagnostic of accretion disk and what happens in the vicinity of this black hole. This is something we talked a little bit about in the lecture about strong field gravity in the last winter. But the reason why I'm telling you all this is that one of the models had predicted that the inner corona in the shape of torus or something like that does precess in a nodal way. So you have the nodal precession of the QPOs, the nodal precession of the inner corona in the shape of a torus that is responsible for generating the quasi-periodic oscillations. So this was an idea that was proposed by Ingram and Dunn back in 2012. And they went even further in the sense that if such a corona precesses, of course, it illuminates different regions of the disk at different times, okay? You see here the lines of constant surface brightness of illumination precessing together with the corona. And this to iron line profiles which change in phase with the QPOs, okay? So in essence, these people went and searched very carefully for a variability of the line profiles in one of these systems, one black hole system that showed that happened to show very low frequency type C QPOs, looking for this effect for variations in the line profile that were associated to the precession, nodal precession of the inner corona. And the outstanding result that they found is that indeed, of course, it's it's marginally significant, but it's very, very interesting, is that indeed there is a difference in the profile. You see the blue profile here, different from the red profile, at two different phases of the QPO precession phase. Okay, these were exceptionally strong type C QPOs and slow QPOs that allow to do phase-resolved spectroscopy, energy spectroscopy of the line profile, of the iron line profile. So this, once again, in relatively recent years, these are works from a few years ago, I mean, emphasize that people trust more and more the interpretation of the low frequency QPOs, meaning HPOs in neutron star and type C QPOs in black holes in terms of nodal precession, as indeed predicted by the frequency identification of the relativistic precession model. So there is never increasing confidence, at least for the low frequency QPOs, that this is the correct interpretation. For the higher frequency QPOs, well, there are those correlations, those nice speeds, those nice values that come together in a coherent way. But of course, we don't have nearly as much information as we have for the low frequency QPOs. And okay, this is basically the same story. And well, I won't discuss this, but it's basically what comes out of the fit to this point here in terms of the profile expected for the two precession phases of the inner corona. Well, I think that, I mean, this trust in the nodal precession interpretation of the low frequency QPOs in neutron star and black hole system that motivated several people. Among them are these two people here, Stushlik and Kolos, to make basically a model detailed model comparison by essentially adding by hand artificially the nodal precession interpretation to models that were not designed originally to interpret also the low frequency QPOs. Okay, so they basically considered the low frequency QPOs of one black hole system, again, the best black hole system from which we have 3 simultaneous QPOs. Okay, and they said, okay, let us consider a variety of models, some that are related to relativistic precession, some that are related to the epicyclic resonance, some others that involve either other things like warp disk or the tidal disruption models that I haven't even talked about. So they basically took this idea, they developed this idea. So models that were developed to explain the higher frequency QPOs, the green and the blue ones. Okay, let us consider this model and up to then the red QPO frequency, meaning the type C and the HPOs, in the same interpretation, this last frequency as the relativistic precession model, meaning the nodal precession frequency, the difference between phi, nu phi, and nu theta. Okay, so this is the variety of model they considered. RP is the original relativistic precession model. Unfortunately, these arrows have now been shifted. I must align them. I'm really sorry. I must have moved this by mistake. So it should really look like this. I will send you a corrected PDF because there are several inaccuracies. Okay, let me display it again. Okay, this is the original precession relativistic precession model. So the upper, lower, I mean the two higher frequency QPOs and the low frequency QPOs here. In application to the three best QPO, simultaneous QPOs we have from a black hole candidate. This one's 1655 minus 40, just these 3 points. Okay, so considering these frequencies, 200, I mean, ones that were used in that paper, and using and verifying whether in this different interpretation, you get values of the mass of the black hole that is consistent with the mass that is determined from the optical observation of this system. Okay. So in this table, you see the different interpretation of the model that were the different interpretation of the frequencies in terms of the different models. Upper high frequency QPO, lower high frequency QPO, low frequency QPO, meaning type C in this case for a black hole. Here, the mass that you derive from the application of this model. Here, the spin of the black hole that you derive. This is which distance you are from the center of the black hole in gravitational radii, and so on. And this is, I believe, a range of masses that you would obtain, and a range of spins that is still allowed. Okay, but let's see. I mean, the relativistic precession model. These are the original frequencies that were used in the model, and you get in agreement with the Motta and collaborators 5.3 solar masses, which is in agreement with this value. Now there are variations on the relativistic precession model that people proposed, and that can work. I will come back to this point, but can work over a limited range of frequencies. Okay, for instance, if you associate the upper kilohertz QPO to nu theta instead of nu phi, the lower high frequency QPO to this difference, the same as in the relativistic precession model, and again this the same as in the relativistic precession model. You get the black hole mass, which is 4.9. This is off already. It's inconsistent with this value. This is another variation of the relativistic precession model. And this, you can see the frequency identification here. Instead of nu phi minus nu r, you get nu theta minus nu r, so it's slight change. And here you get the mass that is still consistent with this value. Okay, now the same exercise for the epicyclic resonance models, different frequency identification. And you see that there is only one version, unfortunately, which is this one here, year one. I'm sorry, this arrow is off. There is only one value, 5.1 plus or minus 0.1, corresponding to this frequency identification, that gives a value that is consistent with this one. I'm sorry, again, I must correct the position of this arrow. Well, let me do it now because it's really embarrassing. Okay. All the others are basically ruled out, let alone this tidal disruption model, which gives you 7 solar masses, or this warp-disk model, which also gives you 7.4 solar masses. So, I mean, just based on the only precise set of 3 frequencies that have been measured for this black hole, if you believe that the low frequency QPOs are generated by nodal precession in some way, and I believe we have by now plenty of evidence that that is the case, well, you can manipulate in different ways the various models, and what you find out is that just the original relativistic model, this variation of the relativistic precession model, and this variation of the epicyclic resonance model give you results that are consistent with this value. Okay, so this emphasizes that just with three precise measurements, you cannot play very much with alternative models. Now, let us suppose that we use, for instance, this interpretation of the relativistic precession model for these QPOs. Okay, so this can work for this single value of the frequency, but in this plot, in this source, which is this one here, okay, we see also this behavior of the green frequency versus the red frequency, and this behavior of the blue frequency versus the red frequency. So, and note that these do extend over a large range of frequencies. So if you change the interpretation, like you do, for instance, in RP2, by replacing, for instance, nu phi minus nu r with nu theta minus nu r, you will not get this, oh boy, behavior any longer. So if you use these 3 points only, you are fine. But if you change the interpretation of that QPO peak, so you don't use the periastrum precession frequency any longer, but you use nu theta minus nu r instead of nu phi minus, I mean, you change interpretation. Now I'm confused on which one they used, I'm sorry. But the low frequency behavior changes completely, and these points are not fitted anymore. So if you use more than those 3 peaks from this source, you are bound to find that they are inconsistent with this interpretation. I'm not sure what to say about this epicyclic resonance model, because, okay, it matches these 3 points, but the epicyclic resonance models, are they capable of explaining such a wide range of frequencies that we see here? I don't think so, because all of this should have to be resonances, and I'm not sure they can explain this as resonance. But here, I mean, you have a continuous variations of frequency. So I think it's difficult to think of an epicyclic resonance model explaining also those very large variations. So let's, well, this is all explained in what I've just told you about these 3 models here is explained in their conclusion here. So this basically brings me to my conclusions, at least on the frequency interpretation in QPO models. So if you believe that black hole QPOs are different from neutron star QPOs, and that the PBK correlation does not hold for the black holes, given that it's almost incontrovertible for neutron stars, you still think of several QPO models as viable models. Okay, you could have models that explain neutron star QPOs, models that explain black hole QPOs at constant frequency, and so on. So there are some models that might still be viable. I'm not saying about physical models. I'm just saying about frequency interpretation. On the other hand, as I've tried to demonstrate in the first hour of this lecture, the similarities in black holes and neutron stars QPOs are probably real and strong, and the PBK correlation holds. Then, to me, but I believe to many people at this point, black hole and neutron star QPOs have a similar origin. I forgot QPOs here, writing QPOs, I must correct this one too. And in this case, the frequency identification of the relativistic precession model is likely the correct one. Again, I don't want to imply that the relativistic correction model, which is simple model, it's a toy model in many ways. I don't want to imply that it is a fruit, that is 100% correct. It is not, because it matches the global feature nicely, but the detailed features sometimes are not matched by the model. But nevertheless, all in all, if you believe that those QPOs do vary over large frequency ranges, that neutron star black holes I mean, neutron star and black hole QPOs have the same origin. Well, at that point, you find that the characteristics of the RPM are pretty well suited to interpret all in all these characteristics of the QPOs. And I think I'm going to stop here. Thank you for your attention and for your patience, because I've spoken longer than I should have spoken.